Electric field. The electric field starts with Coulomb's law. This gives the force between two charges, Q1 and Q2. Similar to the gravitational force, no contact is needed between the two charges for them to feel a force from the other charge. This action at a distance is best understood by assuming that each charge has a field surrounding it that affects other charges. This is called the electric field. Find the electric field due to one charge. The notation in Coulomb's law will be modified slightly, assuming that one charge is very large and the other charge is a small positive test charge that will have a negligible electric field due to its size. The large charge will be labeled capital Q and the small charge lowercase q, and the distance between them is little r. Alright, so we start with Coulomb's law. If we divide the above equation by little q and define the result, we have the electric field. So electric field, by definition, is force per charge. So we have the force here, and charge is little q. The little q's cancel, giving us kq over r squared. The charge big Q creates the electric field. It is a property of the space surrounding this charge. The size of charge Q and the distance to a certain point in space determine the strength of the electric field at that point. E, electric field, is measured in newtons per coulomb. Electric field lines are mathematical abstractions that enable us to visualize the strength of the charge that generates the field and the force that it exerts on other charges that enter the field. When you multiply the strength of the electric field at any point by the charge which is placed there, it gives you the magnitude of the force on that charge. The direction of the field gives you the direction of the force on a positive charge. The force on a negative charge would be in the opposite direction. There are 4 rules to help us draw these fields. Electric field lines begin on a positive charge and end on a negative charge. The density of the electric field lines distribution is proportional to the size of the charges. The lines never cross, or else there would be multiple values of electric force at the intersection point. And the lines are continuous. If there is an isolated positive charge, it will create an electric field that points radially away from it in all directions, since a positive test charge in the field will be repelled by this charge. So here's our main charge creating a field, here is our test charge, and if we place it right here, it will be pushed this way, in the direction of the electric field line. In real life, this would be in 3 dimensions, not just 2 dimensions. The charge creates a spherically symmetric field since it is proportional to 1 over r squared. At any distance r from the charge, the value of the field is the same. Since r can point in any direction, we get the field lines centered on the charge, generating a sphere. Remember, a charge exists in 3-dimensional space. Above, you can see a 3D representation, and below is a 2D representation. If there's an isolated negative charge, it will create an electric field that points radially towards it in all directions, since a positive test charge in the field will be attracted by this charge. So here's our charge creating our field. If we were to place a small positive test charge right here, we could follow the electric field lines and see it would be attracted. It would feel a force to the left. The definition of the electric field shows that the strength of the field decreases as distance increases. So force is proportional to electric field, which is proportional to 1 over r squared. And this can be seen by looking at the density of the field lines. So note that the electric field lines are closer together when you're closer to the charge. So I can draw a circle and there's 3 lines that go through it. If I draw the same size circle out here, only 1 line goes through it. So you can see that the density of the lines shows you the strength of the field. This indicates the electric field is greater nearer to the charge. Excess charge resides on the surface of conductors when they're in electrostatic equilibrium. This is a state where the excess charges are not moving. They all moved to the surface to get as far away from each other as possible. If no charges are moving within the conductor, then there cannot be a net electric force on them. Since there's no net electric force within the conductor, the electric field is 0. E equals F over Q, force per charge. For a conducting sphere with radius r, the electric field is plotted here versus the distance from the center. The electric field is 0 within the sphere. It's at a maximum at its surface, and then it decreases as a function of 1 over r squared. Let's summarize the difference between electric force and electric field. Electric force is the interaction between two charged objects. You need to have two objects in order to have a force. Electric field is the force per unit charge. This equation indicates the net force a positive charge would experience. So electric field, you only need one charged object. A field exists around one object. But for a force, you need two objects.